Hey everyone, good to see you guys. Well, not really, but but I guess I got to talk to you guys. Hopefully, you see me. So I hope you guys can make it to the lecture tomorrow at 11 a.m. On Friday. I'm going to be going over some of these concepts. We're really looking at the problems for the assignment. I'm going to go over all of number one, so hopefully that'll be able to help you out in doing the other three beams. But why don't we get ready? We're going to be going over some old concepts from POE. So if you haven't taken POE, please make sure you watch this closely and ask any follow-up questions as needed. But let's get our structural engineering hats going, because this is actually the culmination of what we've been doing, and this is actually the most valuable. I know in this tough time, it may seem, why are we doing this? If you go into engineering, this is actually a great lesson. This is stuff I learned in my second and third year, and so I really hope you guys take good notes. This will help you out in the future, and so I hope you guys find value in this one. So why don't I give a quick overview of what we're doing so that we understand the concept of this lesson. So previously in other lessons, we've designed the deck of the roof. We used calculations and some code requirements in order to know the loads that are on that building. From there, we designed the beams, but the beams in this situation on the roof were trusses, right? There was a truss system, and that's sometimes available in like larger warehouses. But what do you do if you want to design a steel beam that's just a single member, right? Not a combination of truss systems, but instead one single member. That's what we're looking at in this situation. So we have this floor plan here and a structural floor plan. And we notice that there's all these beams and these girders that are running vertically. The beams that are running horizontal, there are two conditions. There's what we call an interior beam, which is anything that's one, in here, and the exterior beams, which are the ones that are located on the outside edge of the building. Hopefully you already cue into the last lesson where we'd understand that the load that the exterior versus the interior beam is different because of their tributary widths. We also have girders. Girders are like big beams that are now supporting the beams running across, right? So these girders, which are supporting these beams and connected to the columns, on the 3-column line are being placed with withstanding half the load of this side and half the load of this side, whereas the exterior girders only have one beam that's connected to it, right? Well, I guess 3 beams, but one side of it connected. Our goal in this lesson is to select the proper beam. What that means is, what will the size and the dimensions of that beam actually be? And I don't mean the 18 feet. I'm referring to how tall, how thick should that beam be? And we define that by saying something like W12 by 46. The 12 and the 46 are properties of the beam and tells us how tall it is and how thick the beam is. All right, let's get into it. There's going to be 4 conditions, just like I said. In tomorrow's lesson, I'm going to go over the interior beam completely, and then I'm going to leave you guys to go ahead and solve the rest of it, okay? So with beams, there are 3 major conditions we care about. One is bending moment, the other is shear, and the third is deflection. Bending and shear, because the beam is under a lot of pressure, it's going to go ahead and start bending in its max bending moment, could actually cause the beam to break because there's so much compression and tension internally within the beam, the top portion being under compression, the bottom being under tension from stretching, that if there's too much bending, the beam can fail. Equally, if at the ends where there's shear of the reaction force pushing up, but then the load pushing down, that change in shear, or that kind of pressure pushing up or pushing down, whichever it is, that can actually cause a beam to fail too. Just like a pencil, if I put too much shear, it could fail there. Deflection may not cause the beam to fail, right? Bending is what would cause the beam to fail, but deflection matters because if all of a sudden my beam bends too much, well, now I may affect the purpose of the building, right? If there's an office building and it bends and deflects a lot, well, if it, causes everyone to, shift down or people to fall, or, if it affects the building function, then it's considered a failure as well. So in this situation, we've already established design loads, things like snow loads, wind loads. We talked about those. Dead load, live load. We've analyzed the beam. That means calculating the shear and the maximum moment. Today we're going to select the member and make sure it's the right one. Jumping into POE, I want to make sure to cover two concepts that I'm going to discuss, which are stress and strain. So if you haven't taken POE, this is new information. If you have, this is a refresher. Stress is a way for us to compare apples to apples when it comes to force on a member. So if I have a thin metal rod versus a thick metal rod, and they're both made of steel, well, the strength of steel is equal whether it's thin or thick. However, because this steel member is now thicker, it is going to have a higher force that it can withstand before it fails. So what stress does is it allows us to compare the strength of a material and its reaction to force equally comparative to the area of the cross-sectional area of the member. So whether it's a thicker member or a thinner steel member, they're both going to have the same stress because I've compared apples to apples. A formula that you might kind of apply to, I don't know why they use kips in this situation, but kips means 1,000 pounds. So if I have 45,000 pounds placed on a member that's 2x3, how much stress is it under? Well, 45,000 divided by 6 inches squared gives me 7,500 pounds per square inch, which means that every square inch is feeling that much force on it. And that's doesn't matter whether it's thick or thin. And that's just the measure of it, right? And so strain is very similar. If I have a small rubber band versus a large rubber band, but they're both made of rubber, the longer rubber band, the bigger rubber band is obviously going to deform a greater amount. The delta L, the elongation is going to be greater for that long rubber band, but the ratio compared to its original length is the same for a little rubber band versus a big rubber band if they're both made of the same material. So it's a way to, again, compare apples to apples in terms of how much does this stretch or elongate versus its original length. That's what we call strain. And strain is the same for the same material regardless of its size. Stress strain graphs are very widely used in material analysis. So if you decide to go into mechanical engineering, if you decide to go to structural or civil engineering, this is going to be widely used. Even in chemical engineering, it's widely brought up. Any material you create will have something that conceptually looks like this graph where it goes up, then it hits a max, and then it drops down. And I don't want to go into too much detail of why that happens. We kind of covered it in POE, but this is how we generate a concept called modulus of elasticity. It's the ratio of stress versus strain. And what I really want you to take away from here is this important concept, which is the fact that when we look at a stress strain curve, there's this kind of divide between what we call the elastic range and the plastic range. The elastic range means that even though I've stretched the material out and it elongates, as soon as I unload it, means let go of that load or remove the load, it will return back to its original shape, right? That's elastic, right? Just like a rubber band. I can stretch it, let it go, and it'll come back. But everyone's had that little, stretchy rubber band or that, whatever it is that, they kept using it. All of a sudden, it didn't quite come back as much as they thought. And that's because you now reach the plastic range. When I apply too much load onto a member or to any object, right, it eventually will stretch past the elastic range into what we call the plastic range. And that means it's never going to behave the same way again. It's now permanently deformed. And that's the plastic range. And in between those, there's what we call the yield point, and that's essentially the separator between the elastic and plastic range. That yield point is considered the failure point, because as soon as we cannot predict what an object will do, it's failed in our eyes, because now it can react very volatile. It could fail suddenly. We don't know anymore. So we try to avoid any object in structural engineering going beyond the yield point, and that's what we consider a failure point. A lot of people think fracturing is the failure point. It's not. That's just where it finally sheared or finally bent. We don't even want to get close to that, because essentially what can happen is once we can't predict it, then kind of these loads can propagate and eventually lead to a failure at a much lower rate. All right. How do we account for not getting close to that? We create a safety factor, which means that we create a ratio where the safe load compared to the design load is a margin of error. So we say, okay, this has to be a safety factor of 2, which is actually a really huge safety factor. But if I were to say 2, it means you better design this to take 2 times the amount of load than what would cause it to fail. It's kind of like an elevator. When you walk into an elevator and you see maximum load of 2,000 pounds, you would sure hope there's a safety factor, because just in case they do get 2,000 pounds in there, you wouldn't want it to fail. But you're now getting, past the safety factor. So it's kind of dangerous because, you don't know. I also want to make sure that you guys understand that we're using one of two kind of nationally understood methods. There's what we call the ASD method, which is allowable strength design method, and then the LRFD method. These are two schools of thought in terms of how structural engineers should go about it and what the kind of step-by-step process should be. When it comes to steel, ASD is the most common method. And since we're dealing with steel, I'm going to go ahead and use the ASD method. For something like concrete, the LRFD method is used. Conceptually, it's similar. It just has different kind of protocols in terms of what numbers and what load conditions we should be using. But there are two different schools of thought in terms of how you should design, a member in structural engineering. You could read this yourself, but the two things I want to make sure to bring up is the fact that when I say something like maximum safe load, I'm going to say nominal strength. And then when I say maximum allowable load, I might say allowable strength. Okay, so nominal strength, allowable strength, we're going to get into that. So let's look at our formula that deals with those, right? What's the difference between nominal strength and allowable strength? Nominal strength is the maximum safe load that the object can take on. So when I say something like, this omega symbol is safety factor. So when I say the safety factor must be less than or equal to the nominal versus allowable, what we're referring to that is the nominal is saying what is a safe load condition. So something like an elevator can take on, 5,000 pounds. But when I say that the design load, meaning the amount of people that can even physically fit into this box, assuming they're all 6 feet, what's the weight that they're going to load into this elevator? It might be 4,000. So 5,000 divided by 4,000 gives me 1.25. And so my safety factor is 1.25. So what we want to say is the safe range should be that many times greater than what the design condition is going to allow for. All right. So hopefully it'll make sense when we start getting into it a little more. So allowable bending stress. When we compare nominal bending moment versus allowable bending moment, what that means is what is the safety factor that we're considering. So in this situation, the ASD method tells us that bending moment has to be 1.67. What does that mean? It means that the safe load that the beam can hold has to be 1.6 times greater than the load that we should expect based on the given conditions. So if a beam can hold, let's say this beam can hold 100 pounds per se, well, then that 100 pounds better be 1.6 times greater than what we actually expect to ever exist on this beam. So if my load conditions say, hey, there's only going to be 50 pounds of force on this beam ever, maximum. The most people that can fit on this beam is 50 pounds. Well, then now if this can withstand 100 safely, then it's a safety factor of 2, which is good because it's greater than the 1.67. So that's kind of like the margin of how close we should get. How do you even solve for the nominal moment though, right? Because this is an actual calculation. There's a formula that says the nominal bending strength of a beam, so how do we determine how much this can hold, right, is equal to the yield stress of steel. So the yield stress, if you guys remember on this graph, what is the stress at the yield point? So when we look at a stress strain curve, and this is going to be given, so you don't need to calculate this, but when we look at a graph, what is the stress that the steel is under at the yield point times the plastic section modulus? Now, this is something that you're going to be given, so, don't worry too much about it. This is a formula, and you're going to be able to see what the plastic section modulus is. It's dependent on the size of the beam. So it's kind of like saying what's the moment of inertia, right? The plastic section modulus is a property of the shape of the beam times the strength of the beam, right? So where are you going to find this information? So if you click on this link or you copy it, it's going to bring you to this. From here, you're going to go ahead and click on, let me make sure I remember, civil engineering, steel sections. Here we go. Steel sections. Then we're going to be designing specifically W or I beams. We call it wide flange beams because it has a wide flange. It goes like an I, and that causes the flange itself to be wide. So this is what we use in the US essentially. So I'm going to click on that, and that's going to bring me to a chart like this. These are not only the dimensional properties, but also the internal properties of the member. So you'll notice that there's these two tabs up here. And if you scroll down, what this is telling me is if I select the W10 by 45, its nominal weight is 45. That's where this comes from, right? So the second number on a selection of a beam is the nominal weight, meaning every foot, if I cut out a foot of this object, that's how much it's going to weigh. It's 45 pounds. The 10 stands for its depth. So if I look at the dimensions, it actually was on that one. Sorry. If I look at the dimensions, oh no, it's over here. I just think I didn't scroll over or something. Oh yeah, it's right here. So I just didn't look at the right column. So if I look at something like a W14 by 426 or a 14, let's say, let's go here, like a W5, a W6, a W8, you'll notice that nominally it's 8 inches, 10 inches. Yeah, it's a little more, but the 10 is the leading number. You can round up to 10. This is 12, so how tall is the object? So it's just the height of the beam itself. So what we do is, that's one of the columns on there. So if we look at the properties tab, we can actually determine what the plastic section modulus is by looking at the column right here. Okay. So the plastic section modulus that we're using specifically is going to be the ZX axis. So when we look at this, we're going to be focused on this section here. And so because it's bending along the x-axis, right? When it's loaded, it's going to be bending along the x-axis. We're going to be looking at the plastic section modulus along the x-axis, not the y. There's also another formula we have to check, and all this is going to come into play when we actually start doing the formulas and we start doing this problem. But I also need you to be aware of the fact that ASD method requires us to check first the nominal moment, then the nominal shear. What it tells us is that the shear that the beam can withstand better be 1.5 times greater than the shear that the beam will ever experience. So based on the conditions, the shear better be at least 1.5 times greater in terms of the strength that the beam can withstand versus what it's going to experience. How do we calculate nominal shear, right? Just like how do we calculate nominal moment? It's going to be 0.6 times Fy, which is again the yield stress of steel, times AW. AW, which is again the area of the web, is based on D times TW. And those are two properties that are going to come up here. So if I go to dimensions, I think it is, if it's D times TW, then dependent on the beam I select, the D column is going to be right here. TW is going to be right here, right? And we can use the decimal numbers for each one as opposed to fractions. The last thing we gotta do is make sure that the deflection of the beam is not greater, because one of greater than these values. And the reason why we got to do that is because we got to make sure that it can't bend more than what code allows us. So what code tells us is that if it has a plaster ceiling, the dead plus the live load cannot cause the beam to bend greater than L, which is the length of the beam, divided by 240. And that's in inches. So what's the length of the beam in inches divided by 240? For live load, we have to compare it to L divided by 360. If it's non-plaster ceiling, we have a bigger range of deflection, only because when you have a plaster ceiling, if there's deflection of the beam itself, it'll cause plaster to crack. And so that's, not something we want. We have to compare those deflections. So this is what it's saying is it better not deflect greater than this. So one of the things we're going to have to do in our problems is also calculate how much does it actually deflect. All right. So this is an example problem. I'll use it as a starting point for tomorrow's lecture. However, and then I'll go into number 1 on our assignment. However, I'm hoping everyone watches this video, rewatch it. Make sure you've gone through this Google slide before you come in tomorrow. Otherwise, hope you guys take care, and I'll see you guys tomorrow.